So last time, I mean, now we are almost at the end of this chapter, right? There were just one or two things I had to mention. Right, so the last time we proved one statement. So we had this definition of good function, right? And what we proved was, what we showed was that the Fourier transform of a good function is again a good function, right? So, so the main point here was, so if suppose g is a good function, okay, then you look at the Fourier transform g of t, which is 1 over root 2 pi dx, right? So if the gx is a good function, then this quantity, which is a Fourier transform of gx, this is also a good function, right? So this belongs to a good function, implies that this also belongs to good functions, right? Belongs to the good functions. And secondly, the inverse Fourier transform gives you back gx. So if you construct capital GT e to the I tx dt, that gives you back g of x. Right? So this was the important point of the good functions. Okay, so now let's go back to the generalized functions, okay, and try to define Fourier transform of generalized functions. Okay, so again, as we do, I mean, in fact, all the manipulations with generalized functions, what we did was we took the sequence which defines the generalized function. In that sequence, every element was a good function, right? And we did the manipulation at the level of the functions which appear in the sequence, right? So the same thing we will do again. So let's suppose, let's see what symbols. We were using Greek symbols for the, I think, right. So let's suppose there are the sequence of functions f and x, okay, n equal to 1, 2, okay, which defines a generalized function. And we will denote the generalized function by a Greek letter, phi x. Okay. So remember what was the meaning of that? The meaning was that, just to remind you what was the definition of, when we say that this sequence defines a generalized function, what it means is that there is a, for any good function, g of x, the integral f n x gx dx, the limit exists. That is the point. It exists. I mean, this is quite an important condition, you see, because if you just take any arbitrary sequence, this may not have, the limit may not exist. So you're only considering those sequences where the limit of this integral exists for all good functions gx. Then you say that this sequence defines a generalized function. Okay, fine. I mean, this was just to remind you the definition of this. What do we mean by this statement? Okay. Now, take these functions. These are good functions. So these are all good functions. Okay. All of these for each n. So then let's take the Fourier transform of each of them. Right. So let's define the Fourier transform f of n t, which is simply f n x e to the minus I tx dx. Okay. So these are also good function from the previous theorem, right? This is a good function. And now consider the sequence f n t, this sequence. Question is whether this converges to, whether this defines a generalized function. That's the first question, right? So the question is, does this sequence define a generalized function? Okay. So, I mean, suppose the answer was true, answer was yes, suppose it defines a generalized function, then we can define that generalized function as a Fourier transform of this generalized function, right? So, this is the main idea. So, let us see how we can prove that. So, fnt is this here. Okay. So, what we want to start to see whether this exists or not, I mean whether this defines a generalized function, I need to consider an arbitrary good function g of t, right, and consider this integral capital Fnt e to the I tx, right? No, not e to the t. Yeah, I just want to see whether this limit exists. Okay, dx dt. Whether n goes to infinity, this limit exists or not. This is the question, right? If the limit exists, then the answer to this question is yes. So, okay. So, before taking the limit n goes to infinity, let us just consider this integral. Now, g of t is a good function, So, I can write it, in fact, let me use a capital G, okay, because I use the capital F here. So, this capital G, okay. So, the capital G is a good function. So, I take this capital GT and I can always write it as some Fourier transform of a good function. True? Well, you can always do that again from that theorem, right? Because you can first of all construct this object by taking the Fourier transform of this, right? And then we know that inverse Fourier transform gives you back that same function, right? So, you can always construct this function. So, in other words, given this g of t, I mean you have picked some arbitrary good function which I call capital GT. Then I can always construct this Fourier transform, which is gx equal to capital GT e to the I tx dt, dt. Okay. So, define this function. So, this is given to you. You have picked something, one of them. It's arbitrary, but you have picked one. You can construct this by integral. This is also a good function. Okay. And we are also guaranteed that the inverse transform gives you back the original function. So, I can always write this g of t in this form, right, where this little g is a good function. Okay. So, now let us substitute this expression g of t there. So, you find that this is the same as minus infinity to plus infinity. There is a 1 over root 2 pi Fnt and gx. There is another integral. Sorry, here, yeah, gx. So, minus, okay, there are minus infinity to plus infinity. There is another 1 over root 2 pi. No, sorry, that's it. 1 over root 2, I just substituting this here. 1 over root 2 pi there, and then you have e to the minus I tx dx. Okay. Maybe I should use this, I mean, just to get that form. Let me define it like this here, okay, like that. Okay. So, this little g of x just a Fourier transform of capital GT, okay, and then I substitute that back there, I will get this here. Okay. Now, let us, so there is a dt and a dx, two integrals. The dt was here, and this dx came because I substituted capital GT by this expression. Okay. Now, let us first do the dx integral. When you do the dx integral, first let's do the dt integral. Here there is a dx. So, if you do the dt integral and use the fact that the inverse Fourier transform of fnt gives you back fnx, correct? I mean, look at this expression. This part dt and this e to the I tx. This is exactly the inverse Fourier transform. Okay. So, this gives you back fn. So, let me erase this part here. Little fnx, and I have gx dx. I mean, including also this 1 over root 2 pi factor, everything just becomes that, right? Yeah, sorry. I mean, that's not important, right? I mean, here, yeah, no, that is because I just wanted to get back this expression. You see the inverse Fourier transform is fnx is 1 over root 2 pi fnt e to the plus itx dt, correct? So I just wanted to get that expression here, plus itx. Okay, it's for this reason I just defined like this. So I am given a gt, I do a Fourier transform on the yeah. Okay, let's say I just define it like this. This is my definition, right? This is you're giving this to me, and I just define this integral. Fine. Then we know from the previous theorem that this is a good function. Okay, and furthermore, the inverse transform of this good function gives you back the original function. Right. So I'm just using that. And the reason why I changed, before I wrote minus sign, plus sign there, but I changed the sign. It was simply to get this expression there with this particular sign. That was all. Okay. So this is what it is, right? So what essentially the statement is the following. So a capital Fnt is a Fourier transform of little fn, and capital Gt is essentially the Fourier transform with just a flip of the sign. That is all, of the little gx. And we do this integral. That is the same as the integral of the original functions, right? Product of original functions. This capital Fn is the Fourier transform of that. This capital G is a Fourier transform of that, right? And so this integral is the same as that integral. Okay, this is fine. But now, what have we gained from that? The point here, I mean, our original question was whether the limit exists, right? But now look at. But we already showed that this is equal to that. Now this expression has a limit, because by our assumption this little fn sequence defines a generalized function, right? That's our assumption, that this defines a generalized function. So therefore this limit exists. Okay, this was for any arbitrary good function, this limit had to exist. Okay, gx is again just one of those arbitrary good functions. Okay, so this limit exists, and therefore the limit of this integral exists. So the statement is that since the RHS has right hand side has a limit, as n goes to infinity, therefore this implies that the left hand side also. Okay. Because the two things are equal. So this proves that this sequence indeed defines a generalized function. Okay. So this implies that this sequence defines a generalized function, and we shall just denote it by capital phi. That was a small phi, this is a capital phi t. Any questions here? Okay, that was the main point here. And in this case, what we will do is we will just formally we will write. So this is a formally we will write this capital phi t is equal to little phi x e to the minus I t x dx. Okay, but I mean this is a formal expression in the sense that what this really means is that you take the sequence which defines this, consider the Fourier transform of that, right? That defines to you a sequence of functions of t, good functions of t, right? And that sequence again has a limit. I mean that defines a generalized function. That is this generalized function. So it's a formal expression, but it has that meaning. Yeah? Okay. And furthermore, you see, if you look at this expression, this is completely symmetric, right? See, I mean, meaning that if I now take the inverse Fourier transform of this phi t, you will get back the little phi in this sense. Okay, because I mean, here you see the two things are exactly in the same footing, right? So I mean, you start from you take the inverse Fourier transform of fn. That is again, that gives you little fn anyway, right? Because the capital Fn's are good functions anyway. So if you take the inverse Fourier transform, you will get back that, right? And those little fn's, of course, define the generalized function phi x, right? So that means that this means that not only this is true, but even the inverse transform gives you back the original generalized function. Capital phi t e to the I t x dt. Okay, this is also true. So for a generalized function, everything becomes much easier, you see, because for the ordinary functions, you see this was not true in general. The inverse Fourier transform was not generally equal to the same. In fact, when there were discontinuities, it was kind of averaging it, right? The inverse Fourier transform does not give you back the original function, right? Or it gives you only the sense of almost everywhere. You know? But this is exactly true. Okay. So now, now I think the only last point I had to make was now let's go back to delta function. This was a general discussion of generalized functions, right? Now let us focus on the delta function, because that is what you use mostly in physics. Right? The delta function and the step function, these are the two things which you mostly use. So for delta function, we said, so let's go back to the delta function, the Dirac delta function. Okay. So for that, we considered a sequence dn of x, which was just a Gaussian root n over pi e to the minus n x squared, right? This was the sequence we considered, and this sequence defines the generalized function delta x. That is how we said. Okay. Okay, so there are, let's say there are several properties you can see. We can immediately see. So let us take any good function, g of x. Okay. And let us ask the question, what is delta of x, delta x gx? Dx. Okay. I mean, you know what the answer should be, right? It should be just g evaluated at x equal to 0, right? But let us try to understand it from the point of view of this sequence. Okay. Well, this is by definition, it is the limit as n goes to infinity of this integral dnx gx, right? That is a definition. I mean, this is just a formal way of writing it. But what this really means, it is the limit of this, the limit as n goes to infinity of this integral. Okay. So what is this now? So let's explicitly just substitute that. So this is the same as limit n goes to infinity of minus infinity to plus infinity of root n by pi e to the minus nx square dx g of x dx, right? But so in fact, let me consider, I mean, we expect this to be equal to g of 0, right? So let us do the following. Let's take the difference between these two, delta x gx dx minus g of 0, right? We want to, I mean, this is, you expect this to be equal to that, right? So let us see the difference. So what we will show is that, okay, so we'll show that this is 0, the difference is 0. Well, that difference is equal to, okay, this is the first term, what I've written down is the first term. The second term, I can write it like this. correct. Why I can do that? Because you see, g of 0 does not depend on x, I can take it out, and this integral was exactly equal to 1 for every n, remember? I mean, that's how we normalized it in such a way that that integral was exactly equal to 1, right? So it's just I put here 1 times g0, but that 1 I'm writing it like this. It's convenient to write like that. And now let's take the magnitude of this quantity, right? Well, that magnitude will be exactly the limit n going to infinity of this magnitude, right? But that should be less than or equal to the magnitude of this, correct? I mean, it's the magnitude of the integral, right? That's less than or equal to the integral of the magnitude. Okay, so that's that. Okay, but you remember we discussed it already when proving the theorem that Fourier transform of a good function was again a good function. You remember we tried, yeah.
Because J is a good function, G0 equals to limit exists.
Yes.
Here J0 equal 1, I think, no?
Yes, yes.
But with the same J.
I mean, no, all I'm doing is I have a 1 here. I just write this 1 as the integral of dn. That's all. So, I mean, that's a special case because of, I mean, this was true, right? This was integral of dnx dx plus infinity. This was actually equal to 1, right? So I just replace this 1 by that integral. So that times g0, g at 0. But then I rewrite it in this way because you remember in proving that theorem that the Fourier transform of a good function is a good function, in between we use this statement that the gx minus, in fact there I think it was gx minus, say gx1 minus g of x2 in general is less than or equal to the maximum of dg by dx times x1 minus x2. Correct? You remember we used that thing. This was a thing, right? I mean, if you remember, I mean, the way I tried to argue was that if I give you some function, this is at x1 and that's at x2, then if you take the, so this divided by, let me do this divided by that, well, that is simply, if you draw this triangle, this is simply tangent of this angle, right? That this tangent of this angle is going to be less than or equal to the maximum value of the slope between these 2 points, x1 and x2, right? So that was the argument. So I can use that. So just take x1 equal to x and x2 equal to 0. So what this is saying that this is going to be less than or equal to limit n goes to infinity of square root of n by pi dx e to the minus nx square times the modulus of x times the maximum value of dg by dx. I mean, this maximum value I can take it out of the integral because that's just the maximum if I take the maximum from minus infinity to plus infinity, whatever is the maximum value of the slope. And that's going to be a finite, that's going to be not infinite because dg by dx is also a good function, right? So it's going to be something bounded by some number. So it will be some number and I take this out. So some finite number. Okay. And it does not depend on n. That's all the important point. It depends on the g, the good function that we have taken, right? It does not depend on the n here. Now this quantity, you see, well, we can see immediately what the answer is. Well, this is the same because this is an even function. This is the same as 0 to infinity, factor of 2 here, and just the x, correct? Because it's a modulus of x, so it was a good even function. Right? So I can write it like that. And this integral, you can scale the n away, right? I mean, you can do the exact integral of this. Actually, we can explicitly do this integral, right? By change of variable. Dx times x is the same as dx square by 2, right? and then you can do explicitly integral. So this integral is simply 1/2 e to the minus 1 over 2n e to the minus nx square evaluated between 0 and infinity, right? So at infinity it is 0 because the exponentially damped, at 0 it's 1. So it minus minus cancels because the lower limit. So this entire integral is simply 1 over 2n, right? This integral. And you multiply by that, so you get a root n removes a root n from here, but you still end up with a 1 over root n, right? So this result, this thing is the same as 2 cancels, so it's just 1 over root n pi times the maximum of dg by dx. That's what we are seeing with that right hand side. So we see that this difference is 1 over root n pi times max dg by dx. All this is n independent, and I mean I have to take the limit here, n goes to infinity, right? So you see the right hand side goes to 0, right, as n goes to infinity, because there is a 1 over root n here. So therefore this difference goes to 0. I mean this difference is equal to 0. So that proves that this is in fact equal to g of 0. This here anyway new. I mean that was the whole purpose of constructing this delta x, right? I mean that was the whole idea of constructing the sequence. Delta x is something which tells you that they say something is localized completely at one point. That's what is doing here. So this was one. Let me just list some of the properties. So this was the first property, this equation. Yeah, the second property is that if you take delta x and multiply this by any fairly good function, f of x is a fairly good function. Remember, this was true for an arbitrary generalized function, that there is a meaning you can multiply a fairly good function to a generalized function, and again it gives you a generalized function. So let's see, ask what happens if I multiply to this particular generalized function, which is Dirac delta function. Well, the statement is that this is simply equal to f of 0 delta x. It's not surprising again, because delta x is basically non-zero only at x equal to 0. At all the other points, at all the non-zero values, at all x's which are not equal to 0, delta function is 0. The local value of delta function is 0, right? So this is not a surprising result, but you can again explicitly check it. So if you take fx, so what we are looking at again, the meaning of multiplication was you take the sequence which defines delta function and multiply each element of the sequence by this fx. So you take fx times dnx and consider this sequence. This is again a good function, because this was a good function and this is a fairly good function. Product of fairly good function with a good function is again a good function. So this is again a sequence. And let's consider now f of x dnx g of x integral. Okay, that's what. So we're looking at this sequence. So this will define to me this generalized function, right? This will define to me the generalized function f of x delta x, right? So now let us see what is the value of that. What is this object? Well, to see this again, I integrate for an arbitrary good function. Take an arbitrary good function and multiply this, and then take and see whether the limit. I mean, what is the limit? N goes to infinity. What is the limit of that? But that's the same as you see dnx multiplying this good function. After all, fx times g of x is again a good function, right? But this we have already shown that for any good function here, this integral is simply that function evaluated at 0. So therefore, this is going to be equal to f0 times g at 0, because now I'm taking the good function to be this times that, right? Okay. But that is the same as f of 0 times the integral delta x g of x, right? Because g of 0 is the same as that. So that proves that this statement is true, because you see that this was the integral f of x delta x gx, and that is the same as f of 0 times delta x. Okay. I mean, this was almost obvious, so I didn't have to go through that. Now, yeah, okay. Now, so this is one distribution which is useful. Another distribution was the or generalized. Sometimes I say distribution, sometimes I say generalized function. They are the same. Different books actually use different. I mean, some people prefer to use distribution, some people prefer to use generalized function. You had a question? No, no, okay. So there is this step function. Okay, so the step function is let's call it h of x, is defined like this. It's h of x is equal to 1 for x greater than 0 and is equal to 0 for x less than 0. So that the reason why it's called a step is if you try to draw, it's like this here, right? I mean, this is x equal to 0. So here I'm plotting h. That's 1. This is 0. So when x is positive, h is equal to 1. When x is negative, it's 0. So that's why you say it's like a step. Okay. So of course, as a function, this is discontinuous, right? But you can always, I mean, treat it as a generalized function in the sense that you can write down a sequence, okay, which gives you the. So you can write down some sequence. I don't know. I mean, there are many ways of writing it. I think I tried to write it once. So for example, I can consider the sequence like this. Hn equal to tan hyperbolic nx, okay, times. But this is not a good. This has a behavior. You see, tan hyperbolic has a property. Maybe I should put here 1 plus. Sorry, 1 plus divided by 2. Consider this sequence. Tan hyperbolic. What is this tan hyperbolic? It is e to the nx. So tan hyperbolic of nx is e to the nx minus e to the minus nx divided by e to the nx plus e to the minus nx. Right? That is a tan hyperbolic. Now notice that if n times x is positive infinity, I mean goes to positive infinity, large values of nx, this is exponentially suppressed, so you can forget it, I mean compared to that, right? So this simply becomes plus 1, okay? Whereas if you take nx to be negative infinity, then this dominates compared to that. So I mean both these terms I can neglect, right? So you just get a minus 1, right? So in the two limits, tan hyperbolic goes to minus 1 in the negative direction and plus 1 in the positive direction. So that's why I put it as 1 plus tan hyperbolic divided by 2. So this has a property that as this argument becomes negative infinity, this becomes 0, and in the positive infinity, this becomes 1. So this has this kind of behavior. Now, I mean, for that, of course, you have to take nx to be large, right? I mean, for any fixed n, as x goes to infinity, this is the behavior, right? But now keep x fixed and take n large, right? When you take n large, again the same thing happens because n times x will again go to infinity, right? So at any point x, positive x, any point positive x, as you take n goes to infinity limit, you just get plus 1. And for any x negative, as you take n goes to infinity limit, you get 0. So this, so in the n goes to infinity limit, this will become closer and closer to the step function, right? In fact, if you try to draw it properly for any, for n, I mean, this will go like that. It's a smooth function, completely differentiable any number of times, right? But as you take n larger and larger, this starts becoming sharper and sharper, right? But continuous and differentiable and so on. This is going to become sharper and sharper, okay? So, so at all these points, I mean, only problem is at x equal to 0. Everywhere else, this is the regular point of this, I mean, is a regular point of this sequence, okay? And then, so the local value of this distribution would be simply 0 for any negative x and for +1 for any positive x. However, there is a problem. This is not strictly according to our definition. We should have chosen good functions. This is not a good function. See, good function has to go to 0 faster than any power, right? But that's again no problem. You just multiply this by e to the minus say x square over n square, for example. So for any finite n, this is a Gaussian, okay? But n goes to infinity, this simply becomes 1, right? So this is a very easy way of just taking something which is not a good function, but multiply by that, and you can, okay? So these are good functions. Now this was just to say, give an example to show that this h of x can be treated as a generalized function by taking this sequence, and so that will define a generalized function which we will call theta of x. Okay, again Greek letter. I'm using the theta of x. Okay, so we have these two important distributions, generalized functions, delta of x and theta of x. And now, what is the relation between these two? Is there any relation between these two? That's the question. And it will turn out, not surprisingly, that the derivative of theta function is equal to delta function, right? It is not surprising, because after all, if you think about, you can see there is a jump here, right? But now we will see exactly why that is the case. We have already proven before that one of the important properties of the generalized functions was that derivative always exists, and it again gives you a generalized function, right? So let us consider d theta by dx, and consider the integral of this with anything, say g of x dx. G of x is some good function. Let's consider this integral. Well, so we proved actually one thing was that, first of all, the derivative exists of a generalized function, and secondly, it satisfies the usual properties of the integration by parts. It satisfies the usual properties, and that's the same as minus theta x dg by dx. Right? That was the. Okay, let us now explicitly integrate this thing. Well, we know that this theta of x has the local value of theta of x for any negative value of x is 0, right? And the local value of theta for any positive value of x is 1, right? So if I write this integral as minus infinity to 0 plus 0 to infinity plus infinity, okay, then this vanishes, because the local value for any negative x, theta of x is 0, so that vanishes. So all that is left over is that integral, but the local value of theta for positive value of x is +1. So this integral is the same as 0 to infinity of dg by dx, because theta is 1, just 1, constant 1, right? There's total derivative. Sorry, there's a minus sign here. I forgot. There's a minus sign out here. So this simply gives me is a boundary term, the g at infinity minus g at 0. So this gives me minus g at infinity minus g at 0. Okay, g at infinity is 0 because it's a good function. G is a good function, so it vanishes. So this goes out, and we are just left with the minus minus plus plus g0. So this thing is g of 0. Therefore, this is delta. This is d theta by dx is the same as delta function. Right? So therefore, this guy is equal to delta function. So that's a relation between these two distributions. Now I think I've almost finished everything here. The last point is a Fourier transform. So, so we want to find the Fourier transform of the delta function. Of delta function. Well, actually, the dnx that we had written down, which was simply root n by pi e to the minus n x square. Well, this I can rewrite. This is, I think, from one of the examples in the chapter 2. I mean, the complex analysis chapter. It was simply 1 over 2 pi, and the integral of e to the power of I t x minus t square divided by 4n. I t x minus t square divided by 4n dt. This you remember? I mean, you remember one of the things was you have a Gaussian part, but then there is also a phase, right? And that integral you can perform. This was one, I mean, in chapter 2, if you remember correctly. I mean, it's not a big deal. It's just you make it a whole square, right? You try to make it into a whole square. This gives you I. So I want to write it as t. So 1 over 4n t minus I times what should we put? 2n x whole square. You see, I can write this like this. So minus, put your minus here. Yeah. So let's see if you open it up. There's a t square term, which is that. Then the cross term gives you minus 4n x t times I. Right? 4n cancels, and you get minus minus plus. So that's I t x. Right? But this is not equal to that. I have to remove the square term of this. And you remove the square term of that. That gives you 4n square divided by 4n. So n. And then I square gives you minus, 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 plus. I have to subtract it. I have to remove that. So I have a minus here, minus nx square. Right? That's what that is in the exponential. So this whole thing is e to the power of that times e to the that. And you can take out e to the minus nx square, because that's not you're integrating. And this integral, even though it's on a real line, minus infinity to plus infinity, you can move it, shift it to the shift by imaginary part, by this much of imaginary part, and integrate. And the answer is just going to be given by, I think, root, I'm not sure. Yeah, it's root. You have to scale, right? I mean, you have this integral dt. Right? Once you, this is in the real line, but if you move it up, on the by shift by this much imaginary part, you can just call this whole thing as t square. Okay, so I can integrate it by scaling, right? You just take t goes to 2 root n t, right? Change the variable. Okay, so this guy this cancels, and then there you get a root 2 n. Yeah, so 2 root n you get. And then the result of the integral is simply root pi. So this change of measure gives you 2 root n, and the integral is simply root pi. So that's that. Right? And now multiply by that, you get this. Right? So it's just it's a way of rewriting it. But the point here is that by writing it, you see it's clear that this guy is the inverse Fourier transform of this function. I mean, so write it like this. If you take this function, right? So this is a good function. It's the inverse Fourier transform of this function, this good function, right? And so when we discussed the Fourier transform of a generalized function, what we did, we took the sequence which defines a generalized function and constructed the Fourier transforms of those things, right? And see what that sequence defines. So that is the generalized function. Right? So what we are seeing is that from this what we conclude is so if you take this generalized function, I think well, It should be strictly, I think there is a mistake. So 1 over root 2 pi times e to the minus t square by 4n. Okay, consider this sequence. Okay, then this, so dnx is simply the inverse Fourier transform of that, right? Because the inverse Fourier transform, there is a 1 over root 2 pi. So 1 over root 2 pi times 1 over root 2 pi gives you 2 pi, right? So it's this one. So what we are seeing is that the Fourier transform of this dn, dnx, Fourier transforms are simply here, right? The Fourier transform is here, and the inverse Fourier transform goes back there. Okay, so this is some sequence. Let me call it dn, which is a function of t. These are the functions. So this defines a generalized function again. In fact, what generalized function? You can see that as n goes to infinity, this becomes 1, right? So actually, this defines to you a simply 1 over root 2 pi times 1. 1 thought of as a generalized function. So the Fourier transform of delta function is simply some constant. Okay. That's the yeah, I think basically, right, and the inversion formula simply gives you I mean, after all, so this is a generalized function. So what we are saying is that this is the Fourier transform of delta function, right? So therefore, now this object should again be the I mean, so this is what we are saying is 1 over root 2 pi times 1 should be equal to the delta of x times e to the minus I dx, 1 over root 2 pi. Yeah, that's what it is. But this is indeed true. I mean, after all, delta x, it will just give you, I mean, it will just evaluate this function at x equal to 0. But at x equal to 0, this is 1. Root 2 pi cancels, so this is just an identity. You just get an identity. Okay, I think that's about it. I think, yeah, maybe I can just mention one more thing which could be useful in some physics examples again. Sometimes, you know, you get, I mean, so far we've been talking about delta function of x, but sometimes in various physics applications, you find that you encounter something like delta function of a function of x, you see. So let's say y of x. This sometimes it comes like that in some application. This appears like this, but this you can write. So what it is, this is in fact equal to, and I will just write down the equation and then delta of x minus xi divided by dy by dxi, dx at x equal to xi summed over I. Okay, and what are the xi's? Xi's are the roots of this. So so y at xi equal to 0. So that's the definition of xi. So xi's are the set of all those points where y vanishes. Okay. After all, I mean, this is going to give contribution only when the argument vanishes, right? So this will only contribute when y of x vanishes. So that's why it's important to find out where y of x vanishes, right? And xi's are by definition those points where y of x vanishes. So in general, if y is some not a linear function, but some say quadratic function, for example, of x, in general it can vanish at 2 points, right? If it's a cubic equation, it could vanish at 3 points and so on, right? Okay, not necessarily, because some of the roots could be complex, no? But I mean, maximum, if it's an nth degree polynomial in x, a maximum possible number of zeros could be n, right, on the real line. I mean, in general, you could have complex. Yeah. So this I, there could be several i's depending on the complexity of this. I mean, how complicated this function is. Okay. So this is a useful formula, and how do you prove this? So yeah, it's just obtained by, I mean, just evaluating that expression. So you have you want to look at delta of y of x and multiply this to any function g of x, any good function, say g of x, okay, dx plus infinity, okay, and this will be. So let's change the variable, okay. Sorry, this is dx. Let's change the variable from, instead of integrating over x, let's integrate over y, okay. So by change of variable you get, so this is the same as delta of y, okay. Now I just treat y as the independent variable. Now x will become a function of y, right. So this will become g of x of y, and the dx, so this will become dy with a Jacobian, which is simply dy by dx, right, and minus infinity to plus infinity, or whatever the range of y is, okay. But now, of course, the point here is that this is going to get contribution only from, I mean, so this integral will just give you, evaluate this object at y equal to 0, right. But when at y equal to 0, by definition, x are one of those xi's, right. If you want to look at y equal to 0, so question is what values of x gives you y equal to 0, those will be xi's, right. So you will get, this result will be simply g of xi times divided by this dy by dx evaluated at x equal to xi, summed over I. That's what the answer is. So indeed you see that this is the correct. I mean, if you had substituted that, if you had, instead of computing this, if you had directly taken this right hand side and multiply this by g of x and integrate, you would exactly get that answer, right. So that shows you this identity. Okay, I think that's about it. I think that, so we have finished the third chapter essentially. Now, any questions? Yeah. Higher dimension. Yeah, it will be. I mean, exactly the same thing. So I mean, in general, yeah. If you have here, we just had one x and one t, right? If you have several x, let's say x1, x2, x3, three-dimensional, let's say, then you will have also t1, t2, t3, right? So Fourier transform function will be defined again in three-dimensional space. So yeah, but the rest of the discussion is essentially the same. Approximation delta function, it will be, so you just multiply the three. So you have, yeah, for example, you can do this, right? E to the power of minus n x square plus y square plus z square, right? With the suitable power here, okay, of n, and we can determine what the power should be, because we essentially want this integral dx, dy, dz with some suitable coefficient. Let me call it alpha n, some coefficient here which depends on n. This integral should be equal to 1, right? That's what we want. So each of this x, y, z, the three integrals I have to do, each of them is going from minus infinity to plus infinity. Okay. So we can see that now, of course, these are separate integrals. You can just do the x integral, y integral, z integral separately. Each of them gives you a factor of root pi by n, right? So this will give you root pi by n cube times alpha n, and that should be equal to 1. So that tells me what is alpha n. So it should be, this should be simply root n by pi cube. So this sequence will define a delta. So this sequence of these functions will define what we usually denote by delta 3 x minus y, x. There are three, product of three delta functions basically. Okay, so I mean, I have done already. Okay, so maybe if there are questions, we can discuss that. Otherwise, I can move to the fourth chapter, differential equations. About the Laguerre function. Yes. I mean the no maybe it is already given in this what do you call Rodriguez generalized formula, right? Yeah. There is no. No proof of what? Of the differential equation, you mean? The differential equation that I thought, didn't we go through this obtaining differential equation for the Laguerre? Yeah, because the general differential equation was we had obtained, the only thing was to determine lambda n, right? That is maybe I didn't understand the question. No, for the differential equation, I think all you need is just the lambda n. Yeah, I mean, so the differential equation was d by dx. I mean, I'm going back to the equation 10.17, okay, and it was d by dx of SW dc over dx Cn x. This was equal to minus w. So let me divide by w here, minus lambda n Cn, right? Where lambda n was defined as minus n times k1 dc1 by dx plus half n minus 1 d2s by dx2. Okay, so we need to determine this, and what was the s and s was, yeah, here is given here in the table in page 207 table. So for Laguerre, s was equal to x, just a linear, and the weight function was x to the nu e to the minus nu minus x, okay, and the interval was x was from 0 to infinity, okay. So that was the function. So we can compute this the c. It doesn't matter this capital K, because so I mean if I define C1 Cn in general was what was it, 1 over w dn x n w s to the n, right? That was the, with some kn normalization constant. That was as I mentioned to you before, I mean this choice, this kn should not enter. I mean this freedom should not enter in this, right? Because after all, I mean both sides involve Cn only, right? So no matter whatever as a linear equation in Cn, linear differential equation. So I can multiply by any number here, that's not going to change this equation. So the kn should not appear in the, it appears in the recursion relation, but not in the differential equation. It should disappear. I mean eventually, if you have done everything correctly, right, it should not depend on the choice of the kn. Okay, so let's evaluate this. So this so C1, let's look at the C1. It's simply 1 over k1 w, which is x to the nu. So let me write x to the minus nu e to the x, that is 1 over w, and then d by dx of w x to the nu, and s is x, so it's nu plus n, power nu plus n e to the minus x. Yeah. So n is 1, so n is 1, so just nu plus 1. So we're looking at C1. Yeah.
Is the weight function e to the x of nu, because in the table it is given as
e to the minus x, yeah. W is e to the minus x, right? Isn't that e to the minus x? Oh, there is a misprint. It should be e to the minus x. I think yeah, e to the minus nu is a constant, so that would come out. Is it written? I see. There's a misprint then. It's e to the minus x. Because that was obtained, you see already. It should be in the previous page. Classification. Right. I mean, if you look at next to the. Yeah, if you look at this here, this equation is clear, right? Here, this page is e to the minus x here. It's just at the other side of the table. I think there is a misprint in writing the table. Yeah. X to the power of? Yeah, nu plus, but I'm looking at C1 now, n equal to 1. So, yeah, because the C1 I need it here, that's why. So this gives you, okay, 1 over K1. The two terms, one, the derivative hits here, it gives you nu plus 1 times x to the nu, which will cancel with that. E to the minus x will cancel with that. So there's one term which is simply nu plus 1. Another term in the d by dx hits here, so you just get minus. But now you see that e to the minus x will cancel, but here you have x to the nu plus 1. So it will cancel the minus nu, but there is still one x left over. So is that. Okay. K1. So this becomes n minus n times K1 dc1. Dc1 by dx is simply minus 1 over K1, right? So K1 cancels, so you just get minus 1 from this, right? And from here, two derivatives vanishes, so this is 0. For s is x. So it's simply that. It's just plus n, right? Lambda n. And now we can, of course, get the full equation. So you get. So let's take the derivative here. So when the derivative hits here, you get s which is x times d2 cn over dxn dx2, and then you can have derivative hitting s. In that case, w cancels. So you get here plus. So that will come with the d by dcn by dx. And so one term is when derivative hits here, that gives you simply 1. And the second term is when the derivative hits w. So w, if you do that, there will be two terms, nu. Maybe it's better to do this. So what is SW? SW is simply x to the nu plus 1. This quantity is x to the nu plus 1 e to the minus x, right? And that is x to the nu denominator e to the minus x, right? This guy is that. So when the derivative hits here, you just get x term, right? So that's x. Sorry, nu plus 1. Nu plus 1. No, just x. Nu plus 1. So when derivative hits here, you get nu plus 1 times x to the nu, which will cancel. So that's one term. And the second term is minus, derivative hitting here, minus x. Actually, we did that calculation here. I am just repeating. We did that actually just now. So there is that. And then lambda n is n. So you can take it on the other side. So plus n cn equal to 0. That's the. Is that correct? That is the differential equation they get. Laguerre. X plus yeah, correct, plus n, yeah, that's correct, yeah. And what other, you wanted something else also, what, Laguerre, besides the differential equation? If you wanted the computing the coefficients, the highest power of x, I think, right? So for Cn, so that again you can estimate. If you look at the Cnx, that's okay. There is this 1 over kn. That is whatever you choose. Okay. But apart from that, you get here w, which is okay, x to the minus nu e to the x, and then you have dn by dxn acting on x to the nu plus n now times e to the minus x, right? And you're looking for, so we are looking at the, say, largest power of x, x to the n. I mean, after all, this is an nth degree polynomial, so highest power is x to the n. So if you look at the highest power of x to the n, how can that appear? You see, if whenever derivative hits here, it's going to reduce the power of x, right? So if you are only interested in the highest power, then all the derivatives must act on the exponential, okay? And then you get simply minus 1 to the power of n, and then all this cancels. So you see, you get, if the start off is minus 1 to the n divided by kn x to the n, right? Then suppose I want to look at also the x to the n minus 1 term, right? Then what I have to do, out of this n derivatives, n minus 1 derivatives must act there, right? And one derivative acts here, okay? But to do that, there are, so out of this n derivatives, only one derivative must act here. So there are how many ways of doing that? There are n ways of doing it, right? Because there are n derivatives and you're just picking any one of them to act here. Everything else is going to act there, right? So, but I can pick any one of them. There are so n ways of doing it, okay? So you'll get here, there's a factor of n. Then that derivative, when it hits here, it will give you nu plus n, okay? And the remaining n minus 1 derivatives hitting here will give you minus 1 to the n minus 1, okay? And then you're left with the x to the n minus 1. So 1 over kn is outside, so take it out. So you get this, the next one. So this way you can systematically get, if you want two powers less, I mean n minus 2, then 2 of the derivatives must hit here and remaining there, right? Remaining n minus 2 must hit here. So there you have to take, this is a combinatoric issue. So you have to pick 2 of them out of the n. So that is simply nc2, right? So there will be combinatoric factors, and every time this derivative hits here, you will get some other extra factors, like here nu plus n. If there are 2 derivatives, it will give you nu plus n times nu plus n minus 1. So this way you can get the full thing, I mean, step by step. You can get. Okay. So if there are no other questions, maybe I move on to the 4th chapter now. Some differential equations. Okay. Right. So I mean, there's a general. So again, I'll be, in fact, I'll be entirely talking about again one variable problem. Okay, only one variable problem, not the partial differential equations. Yeah, something else. Yeah. For the
complex plane. Can you talk about the Fourier transform in complex plane?
Fourier transform. Complex plane, I would just take it as a two real x and y, because you cannot. I mean, that will be more complicated because I mean it could exponentially blow up. No, I mean, if you're just going to put a phase. I mean, see, this one was oscillatory. So long as you have x is real, it's oscillatory only, right? But if suppose I had put here some z, that could blow up, right? I mean, for say. Take say suppose it was just x equal to 0, so just iy. I mean you have x plus iy. No, then so there is a real part which is minus ty. So this is the same as e to the minus ty times e to the itx. Okay, this is just oscillatory. But so if I look at the magnitude of this thing, you see the magnitude of that's that, because this is 1, right? And now depending on the sign of y, I mean if as t, I mean this can blow up exponentially. So it's always done with the real. The Fourier transforms are always done with the real. Okay, so I will be considering only one variable. So my variable will be always one variable problem. So one variable, let's say x, and we are considering functions of x. So this is very restricted class. A lot of physically interesting things are not captured here. For example, all these partial differential equations you have seen in the hydrogen atom problem and so on. No, those I'm not touching. I'm just touching the one variable problem. If in the end I get some extra time, maybe I discuss again spherical harmonics, because I think you have seen it, but it's always at this stage it's always good to have a repetition. No, so but if I get some time in the end, I will discuss spherical harmonics and so on. But let's see. Usually I never get time to even finish one variable problem, so I don't know. Okay, and so of course, let me just start with some generality, although I will come down to just a second order differential equation, linear second order differential equation. Okay, but to begin with, let's just discuss some generality. So a differential equation is generally a function like this, which depends on, say, some function u, its derivatives, up to some nth derivative. Okay, there is some function which depends on, whose arguments are u, first derivative, second derivative, all the way up to nth derivative of u. And say we are demanding that this is equal to 0. So that's a differential equation. In fact, it could be nonlinear. I mean, this is just general statement. If I am given some algebraic equation which involves as variables u and first n derivatives, okay, and then that is supposed to be equal to 0, then this is a differential equation. And it's called of nth order, of this what's called of nth degree. Okay, I think nth order differential equation. This is capital N. Okay, that's what it is. Now, how will we? I mean, if you give me something like that, how will we'll try to solve this equation? So we want to determine what is u. I mean, so this is a basic question. So let me try to rewrite this equation in the following way. I mean, of course, after all, I can always solve this equation, this algebraic equation, in this n plus 1 variables, right? There are n plus 1 variables, so this is some algebraic equation. And suppose I can solve for dn u by dx. So I solve for dn u by dx n, right? That will be some function of all the remaining variables, right? So it will be some function of u du by dx all the way up to dn minus 1 by dxn minus 1 u, right? So this is because this if you think of this as independent variables, this is just an algebraic equation for this n plus 1 independent variables, right? One equation. So I can always solve for say one of them as a function of the remaining guys, right? So this I can do. Okay. Of course, in general, if it's a nonlinear equation, this could be this could come with some power of this guy. No, in that case there could be many roots of that. But let me just for simplicity assume that I just picked up one root of that, and I can write it like this, right? If there are many roots of that, there will be several possibilities. This will be one possibility, then another root will give you another possibility, and so on. Right? So choose one of them. Okay. Now, so I mean, how will I try to solve such an equation? Well, in order to solve some equation like this, I need to specify these values, right? If I need to specify these values at some point, then this equation will tell me what is the value of this, right? So let's take some point x naught. So let's suppose at x naught I have given the value of u, the value of the first derivative of u, okay, and so on, all the way up to dn minus 1 dxn minus 1 u evaluated at x equal to x naught. So let's suppose I have already given you these numbers. There are some numbers now, right? If I give you this number, I can plug these numbers here and determine what is dn u, nth derivative of u. Okay, so I need to give this data. Okay, if you give me this data, then this equation I can use to determine the nth derivative. In fact, you can determine any number of derivatives recursively, right? Because once I determine nth derivative from this equation, then I can just take one more derivative of this entire equation, right? If I take a derivative, one more derivative, I'll get dn plus 1 over dxn plus 1 u, and on the right hand side, you will get what? You will get some function of u all the way up to n minus 1 derivative, plus together also with the n derivative, because you see you are applying one derivative here. So when I apply one derivative, you can convert this to dn derivative, right? So this will be another function, let's say h tilde, of which depends on u all the way up to dn u by dxn, right? So this way you can keep going, right? But the point here is that I use this equation. I mean, this if somebody gives me this data, right, then I use this equation to determine the nth derivative. Then I use this equation to determine n plus 1th derivative, and so on. So you see, all derivatives I can determine. I mean, as much as I want to, as much accuracy I want to, I can obtain, right? And that means I should be able to find a solution in the neighborhood of x naught. If I know all these derivatives in some kind of Taylor expansion, I should be able to determine the solution in the neighborhood. Assuming, of course, all well behaved. I mean, there could be singularities and so on. But for a regular, I mean, in a situation where there is no singularity, this data should be enough to determine a local solution in neighborhood at some point. Now, of course, this is a bit, I mean, one has to worry about all these singularity issues, etc. And I will just state a theorem. And the theorem says the following. So what the theorem says is that if you give me such a thing, and if H satisfies some condition, okay, then a solution exists. Okay, there is also existence. So again, I just state this theorem. So the theorem is that if H H as a function of these variables. So how many variables are there? There are n variables, right? N variables in the sense that u, du by, I treat them, think of them as independent variables. So 1, 2, all the way up to n. So this depends on n variables. So if H satisfies a condition which is called Lipchitz condition, Lipchitz condition, and I will just define to you what that condition is. So a condition in these variables, in those n variables. So in general, a condition is stated in the following way. If I give you a function of, say, n variables, y1, y2, up to yn variables, and so consider now some interval. Okay, this is n variables, right? For each of this variable, I consider some interval, right, where this variable is allowed to move, to change, vary. So let's suppose yi is between greater than, let me call it ci minus eta up to ci plus eta. Okay, so ci is some number, and so the interval is specified by eta, right? So the yi's are ranging from, so if you draw a picture, ci is some number here, ci plus eta is this, and this is ci minus eta. Okay, so the full interval is length 2 eta, and yi is supposed to be inside this range. So you are allowing this function, these variables to, this yi's to go between this range. So they are kind of a box, I mean a big hypercube, I mean in this n-dimensional hypercube, which is centered at this point ci's, but the length of this, each side of this box has a length 2 eta. So these points are inside this range, and so we are considering this. So what is this condition now? The condition is the following. So if I take f of say y1, y2, and then take the yk, yk, let's say let's call it yk prime, and keep everything else. So yk plus 1 up to yn. So I consider now the function f evaluated at these points yk, okay, and another point where I keep all the other coordinates, all the other variables fixed, and only change the yk to yk prime, where of course both yk and yk prime are in the appropriate range. So inside that range where you are allowing these variables to move. So if I do this, then the difference between these two, absolute value of the difference between these two, is bounded basically. The statement is this. So let me write it explicitly. So if the absolute value of this is less than or equal to some number yk prime minus yk absolute value times some number, I don't know, some whatever. Here is used k. Unfortunately, I use a k here, so I don't want to use the same k. Let me use a capital K. Okay, some number, but k is some finite number. Okay. So what it is? I mean, okay, this looks a bit weird. I mean, a horrible looking thing. But what basically one is saying is that this f doesn't change too much in that big. I mean, this box that we have defined by this here. I mean, just to give an example, let me try to suppose this capital N was just 2, right? So there is just y1 and y2. So what it is saying, so I have so y1 and y2, this is a y1 direction, that's y2 direction, okay? And so this point is the point which is C1 and C2, okay? This point is C1, C2, and you are looking at a square of length 2 eta each. So this is my box, and I am allowing this y1 and y2 to move inside this. So I am considering this region. Okay, and what this condition is saying is that this function of y1 and y2, as I change, say keep y1 fixed, and I change y2 from here to there, then the difference between the function evaluated at this point minus the function evaluated at that point, absolute value of that, is less than or equal to some finite number times the distance y1 minus the distance between these 2 points, right? Similarly, the other direction. So essentially, this is basically saying that f is not going to change violently, right? In this box, f is just going to change, but not too much. I mean, it will change by some finite amount. It won't be. I mean, in general, it won't be true. I mean, if f was some singular function, suppose this function f had some singularity here. That would not be the case, right? In this box. Right? So this is essentially saying that function f is not going to change violently up. No? It is going. Yeah. Yes. Yeah, correct. Yeah, exactly. So okay. So basically, Lipchitz condition is that's what Lipchitz condition is basically saying that this there is some box around some point C's labeled by C1, C2, etc., where function f it doesn't change too much. I mean, it's not going to just blow up or something. So if this h considered as a function of these n arguments, right? I'm just calling this as y1, y2, of yn, right? If it satisfies the Lipchitz condition, then there is a solution exists. A solution exists and is unique. Okay, so in other words, so let's suppose so unique in what sense? So let's say I have some x inside x naught. X is equal to x is in some interval, say a b. Okay, and x naught is in some interval. In this interval, x naught is some point here, and these c's. What do I mean by these c's? C's are just the values of these n variables at the point x naught. Okay. So what we are saying is that u of x naught is C1, say du by dx naught dx at x naught is C2 all the way up to dn minus 1 u by dx n minus 1 evaluated at x naught is equal to Cn. So if around this point in this n dimensional box, this point, if there is a box of some finite size, eta is some finite number, could be a small number, doesn't matter. If the small, then a solution exists to this equation. A solution for u exists. I mean, this differential equation, and it is unique. Okay, that's the statement. Okay. In a neighborhood, of course, around, in a x in a neighborhood of x naught, it will be the solution exists. Okay, this is a theorem, but I mean, in some sense. Yeah, I mean, basically what this kind of a condition is saying that there is nothing singular happening. So you are looking at these are called initial conditions. So at x naught, u satisfies these conditions. Then in a small neighborhood of x naught, the solution can be determined by the procedure I outlined before. Because this equation tells you what is n derivative. Then you take one more derivative, so you determine n plus 1 as the derivative. So you determine all derivatives in that neighborhood, at that point, and then of course by Taylor expansion you can, write down the function nearby. But in doing so, one is assuming that nothing drastic happens. I mean, when you start taking derivatives, you don't hit some singularities and so on. No? And this Lipchitz condition is basically making a precise statement about it. What do you need to ensure there is a solution? But okay, so that is the thing. Right now, okay. I mean, so this was of course one type of boundary condition, because what is happening here? This is at a given point, I am giving you the function, its derivatives, all the way up to n minus 1 derivatives. Why n minus 1? Because I am considering nth order differential equation. Right? For example, if it was second order differential equation, suppose capital N was 2, which is the case we will be studying entirely from now on. We will be always studying second order differential equation. So n is equal to 2. In that case, n minus 1 is simply 1, which means just the function and its derivative, first derivative at a given point. But it need not be. I mean, you don't need to. Many times in physics, that's not the way a differential equation appears. Sometimes you have the values of the function at 2 points, right? Say which is called Deschler boundary condition, or you may have a Neumann boundary condition, things like that. No, you can have. So it's not just one point. Many times it happens you have 2 points. There is an interval. You want to solve differential equation between that interval, and at these two endpoints you have some boundary, one boundary condition here and one boundary condition there, right? But altogether you must have 2 boundary conditions. That's the main point. You see, for a second order differential equation, you need 2 informations, 2 numbers you need. But that number you could either choose at the same point or at different points, but the total information you need is 2. In an nth order differential equation, you need n data. So that's the main thing. So I mean, in general, a differential equation could be of the following type. I mean, so suppose I am trying to solve a equation in some interval. Suppose x belongs to some interval a b, and so from now on I will always consider capital N equal to 2. Okay, maximum 2, not more than. If capital N equal to 1 is a first order differential equation, that's a trivial thing, right? But so capital N equal to 2 would be the interesting case. So in this case, I need 2. The data is 2 data, but you can choose a more general boundary condition in the following way. You have u at a and u at b, the 2 endpoints. So, and the first derivatives du of a at x, du of dx at a, and du x equal to a, and du by dx at x equal to b. These are the like 4 data. But I mean, you don't need all this 4 data. In fact, that will be over determining this system. You need just 2, right? So that data could be any possible 2 linear equations, u at a plus du by dx, I mean some alpha, let me use the same symbol, alpha 1 times beta 1 du by dx at a, at x equal to a, plus gamma 1 u of b plus delta 1 du by dx at x equal to b. That is some number, say sigma 1, and another alpha 2 u of a plus beta 2 yeah. So just 2 equations. X equal to b equal to sigma 2. Okay. So you see what I'm saying here. I mean, I give you 2 linear equations involving these 4 unknown quantities. Okay. So these 2 equations will determine 2 of them out of these 4 guys. 2 of them you determine, right? By the way, I mean, I'm assuming that these 2 equations are linearly independent. Okay. So assuming that these are linearly independent. Then using these 2 equations, you can determine 2 of them, right? But that is exactly what I want. I need to have a data of 2 information, right? So that's the, as an example, let's say I can choose, for example, beta 1, gamma 1, delta 1 equal to 0, and alpha 1 is, say 1, okay? Then that just tells you u of a is sigma 1. So, and similarly, you choose beta 2, gamma 2, delta 2 equal to 0. No, it should be linearly independent. So let's choose alpha 2, beta 2, gamma 2, delta 2 equal to 0, right? That tells me that, and gamma 2 equal to 1, that tells me u of b equal to sigma 2, right? So that will be the situation of Dirichlet boundary condition. The value of u is specified at the 2 endpoints. So, or if you want Neumann, it's called, and the Neumann boundary condition, you can choose, for example, all these guys 0 and that 1. So, and say sigma 1 is also 0, then that tells you du by dx equal to 0 at x equal to a, right? And similarly, if you choose these 3 0 and that one not 0, and sigma 2 is 0, it will tells you du by dx at the other endpoint is also 0. That will be Neumann. But in all cases, you need 2 informations, right? How you distribute that information between point A and B, there are many ways of doing it. And that is what all these unknown, I mean, these coefficients, alpha, betas, gamma, delta, etc., reflect. You have many different ways of choosing boundary conditions. Okay, so that's that. Okay, so from now on, so let's now we'll let me see how much I can do, maybe. Again, I mean, so going back here, you see, I mean, these coefficients, these numbers I chose arbitrarily, right? Changing this, and given this number, I find a solution. I mean, what this theorem, Lipchitz theorem is saying that, I mean, the theorem is saying that if this function h satisfies Lipchitz condition, then a solution exists, a unique solution exists, which will of course depend on these numbers, right? Now, if you change these numbers, you'll get another solution, right? So there will be many, in fact, the number of solutions is parameterized by these n numbers, right? So there are many different solutions to a differential equation. Just, I mean, so for each choice of boundary condition, you'll get one solution, right? In this language, that's what it means. For each choice of boundary condition, you'll get a solution. But you change the choice of boundary condition, you'll get another solution. But I mean, in general, you cannot say much about it. When you have a, I mean, this function h could be a nonlinear function, nonlinear, meaning maybe the square of this guy appears or product of these guys appear. No, so that could be highly nonlinear. But that's a very difficult. I mean, it's very difficult to solve really nonlinear differential equations in general. So that's so I'm not going to discuss about that. I'll be only discussing linear differential equations. So we'll restrict from now on to n equal to 2 and linear differential equation. Linear means that all these function and its derivatives appear linearly. There are never products of these guys. So linear differential equations. So the most general linear differential equation for the second order is of the following type: ax d2 u by dx2 plus bx du by dx plus cx u. I think there's a misprint, by the way, in this. In equation 2.6, the u is missing. Equal to, so u is a function of x, of course. U is the function which you need to determine is some q of x. So this is the most general linear second order differential equation. You see, linear, that's the important point. That's why I'm able to write such, if there's a nonlinear, you could have products of these, no? That would be additional pieces or cubic or whatever, you can have. But for linear differential equation, that's what it is. So you have four functions, a, b, c, and q. Okay, so this is called a linear differential equation. But there is a further classification. If q of x is 0, right hand side is 0, then this equation is called homogeneous. Then this is called homogeneous linear differential equation. And if qx is not 0, then it's inhomogeneous. Okay. That's just a terminology. Just when somebody says a homogeneous differential equation, it means that's 0, basically. Right? So homogeneous differential equation has one property, that a trivial solution always exists. U equal to 0. That's always the solution of that, right? Of the homogeneous differential equation. Furthermore, what is interesting is that if I give you two different solutions of this equation, then any linear combination of these two is also a solution. Correct? That's only true for homogeneous, not true for inhomogeneous, right? So if you have a homogeneous linear differential equation, then if you give me two solutions, suppose u1 and u2 are solutions of this equation, then any coefficient alpha u1 plus beta u2, x. Alpha and beta are constants, not dependent on x, is also a solution. Right? Obvious. That's only for the homogeneous. For q of x is 0. So what is nice about this homogeneous linear differential equations is that the space of solutions is a vector space. Right? Because you see there's a vector space structure. That is a nice thing about it. And it will turn out, we will see that even the solution of inhomogeneous equation you can determine if you know how to solve the homogeneous differential equation. Okay? So we will first focus on the homogeneous, and then we will try to see how one can write down solution for inhomogeneous equation. That's the okay. So now maybe I should just stop here now. Okay, I will just first do even before discussing n equal to 2, I will discuss next time. But let's just look at the n equal to 1 case, the simplest case. That is the n equal to 1 case, is the first order differential equation. So the only term is a of x du by dx plus b of x u of x equal to, say, f of x. This is now inhomogeneous. I'm considering a more general inhomogeneous. First order differential equation is always very easy. And the way to solve this is, one systematic way of solving this is to write, say, b of x over a of x I mean, these functions are given to you, right? I mean, only unknown quantity is u. A, B, and f are given to you, right? So take this ratio b by a and rewrite it as 1 over px dpx by dx. Okay. So this is a definition of p. So I mean, of course, you can solve for p. What is the solution of p? I mean, this is the same as d by dx of log dx, right? That's the same as that. Okay. So I can solve this, say, for example, log of px, therefore, is just the integral of b of x over b of, let's call it y, over ay dy from some point, some fixed point x naught to x. Right? This is the solution. No? I mean, just look at this. If you just take d by dx of that, you just get this, right? So that's a solution. And therefore, p of x is exponential of this thing, exponential of x naught to x b over a dy. Okay, times any constant, any constant you can put here, some constant, because that constant anyway drops out from here. Any constant you can put, that will be a general solution. So once you have done, so once you have found p, now how I go about solving this original equation. Okay. So let us substitute for the b. Let's use this equation to substitute that. So you find that the first equation becomes a du by dx plus, well, b I have to multiply by a here, right? So you get here a over p dp by dx times u, right? That's equal to f. I just stopped writing. These are all functions of x. Okay, they are not constants. They are functions of x. Okay, now you multiply by p and multiply the entire thing by p and divide by a. Okay, so you get here p du by dx plus dp by dx u is equal to pf over a. Right? So I just multiplied this entire equation by p divided by a. So you get that. But this expression is a total derivative. So this is simply d by dx of p times u. Right? Left hand side. So once again, I can integrate this out. So p of u, p times u at x is simply integral of p y fy over ay dy from some point to x naught to x, right? So that way you have solved basically. So u of x is simply 1 over px times that. So this is just a systematic way of finding the solution for this u. So what has happened? First of all, you determine p of x. This is written a, b, and f are given to you. So you just take b over a and integrate it between 2 points. X naught is some fixed point up to x. Okay. Yeah. Correct. Yeah, correct. Yeah, that's the solution of the homogeneous differential equation. Yeah. And then using this p, so exactly. So this is the solution of the homogeneous equation. If f was 0, that would be the u would be simply that, right? And once you know this homogeneous solution, then you plug that in here, and you find the u, the solution of the inhomogeneous equation. Right? Yeah. Pf over a, yeah. I mean, this is, so we are, the equation is this is equal to Pf over a, right? So I can now write so the solution of this equation is simply Pu is equal to the integral. It's an indefinite integral, you see. It's not definite integral. This x is the same as this x. From some fixed point, you can choose any point. It doesn't matter what point you choose. X naught to p of this guy, P of whatever this appears here, right hand side, Py Fy over A as a function of y dy. I'm integrating. How do you prove that? Well, take derivative on both sides with respect to x. So this derivative is the left hand side here, and there the x only appears in the limit point. So when you vary the limit point, what you get, that simply gives you the integrand at that point, right? So the integrand at that point is this, because this is all at x. I mean, I stopped writing x here, but remember this all is a function of x here. This is all function of x here. Okay, everything, there's x everywhere. So this is also a function of x. This also, everything is x. Yep. So that's the way to. Yeah, this is a, okay, maybe I will just stop here and then we go to the second order next time, Thursday. Yeah. Yeah, I mean, so we are. I'm talking about. I'm integrating it in a region where A, B, and A and B, particularly A, is not 0 in.
What happened in this region? Then what when our x branch?
Okay, then you have to worry about the singularities and so on. Yeah, but I'm assuming for the this discussion is a very general discussion in the sense that I'm assuming that there's just normal situation, not no singularities. I mean, we will come to the singularity in detail later. When we discuss second order differential equation, we'll see that. In fact, essentially the solution will be basically characterized entirely by the singularities. We will see that. But for the moment, I'm just assuming that all this is in a region where A doesn't vanish. Otherwise, if A vanishes, then there would be a problem, right? Yeah. Actually, I mean, maybe I should say, actually it's not P, it's 1 over P, I think, right? Because if f was 0, what this equation is that this is equal to 0, right? So u, u is equal to any number divided by P is a solution, right? Any number divided by P. And in fact, you can see that's an arbitrariness here, because anyway, if I find a particular solution of this equation, to that I can always add a solution of the homogeneous equation. That will still be a solution, right? But indeed, and that ambiguity is coming by, because if I change x naught, right? I mean, so let me suppose I change x naught. So instead of considering this solution, I consider a solution where u of x equal to 1 over px, some not x naught, but some x naught prime to x. This is also, but this was completely arbitrary, this point, right? I could have chosen another point. And what's the difference between these two? You see, what's the difference between these two is simply I can write this integral x naught, I can write x naught prime to x as the first from x naught prime to x naught, and then plus x naught to x, right? This part gives you back this solution, right? But from here to here, when you do the integral, whatever the result of the integral is will not depend on x. So it is going to be some number, right? So some number divided by px. That is a homogeneous solution. 1 over px is the homogeneous solution. Sorry?
If you take fx equal to 0, you can see that
Yeah.
the px is the inverse of it.
Exactly. Yeah. From this equation already, yeah, you see. Okay. So from next time we'll go on to the more interesting case.